So welcome to Advanced Higher Chemistry. We are starting on Unit 1, and the first part of Unit 1 is all about inorganic chemistry. And the first part of inorganic chemistry is looking at atomic spectroscopy. So the first topic we're going to look at is electromagnetic radiation, which will lead into atomic spectroscopy. Now, electromagnetic radiation is quite a large array of different types of radiation. Visible light is just a small part of this wide spectrum, and visible light is all the colors that we can see. So included in electromagnetic radiation are things like radio waves, microwaves, infrared, visible light, which is in the middle, then ultraviolet, X-rays, and gamma rays. Each type of radiation has a different wavelength, and as you can see going from the radio waves on the left to the gamma rays on the right, that the wavelength, which is the distance between two peaks on a wave or two troughs on a wave, that is getting smaller as we go from radio waves across to gamma rays. The wavelength is getting smaller. Now, wavelength, when we're talking in chemistry, the main types of radiation that we're thinking about is infrared, visible, and ultraviolet. And when we're dealing with those three types of radiation, we usually give our wavelength in nanometers, sometimes in meters, but it's more common to give it in nanometers. And 1 nanometer is 1 times 10 to the minus 9 meters. When we're working with visible light, we're mostly thinking about 400 to 800 nanometers in length. So that would be 400 times 10 to the minus 9 to 800 times 10 to the minus 9 meters. Now, all electromagnetic radiation travels at the same speed, which we call the speed of light. And the speed of light is known by the letter c. And the speed of light, c, is 3 times 10 to the 8 meters per second. The very back of your data booklet has this written as a constant. C equals 3 times 10 to the 8 meters per second. Wavelength and speed are related to one another by the relationship that C equals F lambda. So the speed of light equals F, which is the frequency of the wave, multiplied by the wavelength. And F is frequency. Frequency is the number of waves that pass through a point per second. And its units are per second or sometimes hertz. And each type of electromagnetic radiation will have a unique wavelength and frequency that multiply together to give the speed of light. Now, when we discuss electromagnetic radiation, particularly light, we usually think of it as being a wave. However, electromagnetic radiation can also act like particles. And particles of light are called photons. When a photon is emitted or absorbed, energy is either lost or gained by the object that is receiving or emitting that light. And the energy, the value of that energy, is equal to h multiplied by the frequency. Now h equals hf, or E equals hc over lambda. Now whenever you're using this equation, you need to turn your wavelength into meters. So remember that 1 nanometer is 1 times 10 to the minus 9 meters. You need it to be in meters, and the Planck's constant h has a value of 6.66 times 10 to the minus 34 joule seconds, not joules per second, joule seconds. And so you can tell it's a very, very, very small number. Now, if we use Planck's constant, we get an energy value that's in joules, and joules alone. In chemistry, we want joules or kilojoules per mole. So we need to modify the equation. So when we modify the equation, you can see each of these equations has had two things added to them. And we've got divide by 1,000 at the bottom. So dividing by 1,000, that is how we turn joules into kilojoules. We can also see that each equation contains a capital L. And that capital L is Avogadro's number. And Avogadro's number tells us the number of molecules that make up 1 mole of a material. And it is equal to 6.02 times 10 to the 23 per mole. Now the data booklet, on the same page that has the speed of light, you'll also find Planck's constant and Avogadro's number on the same page, page 22 of the data booklet. So you do not have to remember these numbers. However, if you are able to, it will save you some time during the exam. And as I said, the reason why we divide by 1,000 is to turn joules into kilojoules. The equations for calculating energy given in the data booklet do not have this divide by 1,000 step. So you do have to remember to do that for calculating things in kilojoules. So we have got a few questions just to finish up this. So there are questions for you to have a go at, pause the video, and when you unpause the video, I will go through the answers. So I'm hoping that's everyone unpaused the video and wanting some answers. So the first question is, what is the energy released by 1 photon of wavelength 420 nanometers? Now I asked for the wavelength of 1 photon, not a mole of photons. So we're using A equals hc over lambda for this. You needed to convert 420 nanometers into meters, which is 420 times 10 to the minus 9. And when you do the equation, you should get 4.74 times 10 to the minus 19 joules. What is the energy released by 1 mole of photons with a frequency of 5 per second or 5 hertz? Well, I got 2.00 times 10 to the minus 21. Now for that one, it was 1 mole of photons, so the equation you were going to need to use is A equals LHF divided by 1,000. And for the final one, if the energy released by a mole of photons was 400 kilojoules per mole, what is the wavelength of the photons? So it's 300 nanometers. For doing this, you would be starting with the equation E equals LHC over 1,000 lambda and reorganizing it to find lambda, which would be lambda equals LHC divided by 1,000 multiplied by the energy. You probably would have got an answer of 3 times 10 to the minus 3 times 10 to the minus 8, which is the equivalent of 300 nanometers, or 3 times 10 to the minus 8 meters.